In the final part of this lecture, I want to lay the groundwork for a new topic within the general theme of causal inference. And that topic is directed acyclical graphs, or DAGs. A DAG is not a method of estimating causally relevant parameters, but it is a way of representing a set of causal assumptions. Therefore, it helps clarify our thinking about causality. It does this by giving us a set of rules for identifying causal effects. In particular, if we want to identify a causal effect, a DAG tells us which variables should or should not be conditioned on. Even though they are expressed in rather different ways, there is a formal equivalence between DAGs and the potential outcome framework. But we need not concern ourselves with this further, other than to note that they are compatible with each other. One thing that the DAG way of thinking about causation does is make us confront the fact that causes do not magically emerge out of the process of drawing a DAG. The causation comes from us, from the assumptions we are willing to make. Another way of putting this is to say that if we start off with the assumption that T causes Y, then a DAG will tell us what we need to do to correctly estimate that causal effect. We can't get causes out of a DAG, or in fact out of any method of thinking about causation, without putting them in ourselves. A DAG consists of a set of directed line segments. That means lines with an arrow at the end. These line segments set out our assumptions about what causes what. Each line segment points from something to something else. Where they come from and what they point to are called nodes. Nodes are sometimes represented by dots or small circles. In this figure, I've dispensed with that convention and simply represented the nodes with letters. The letters represent the variables in the causal system. A line with an arrow at the end of it pointing from A to B means that A causes B. In a DAG, the arrows normally always have an arrow at just one end. This means that they do not deal with the kind of feedback loop system in which A causes B and B causes A. We can build up a DAG to represent our ideas about a system of causation by using a small set of building blocks, most of which we've already met before. Panel 1 represents a chain of mediation. A is a direct cause of B, and B is a direct cause of C. This system has the following implications. Firstly, A and C are marginally dependent. This means that if we ignored or weren't aware of B, we would observe that A and C are associated. Secondly, A and C are conditionally independent given B. This means that if we control for B, then within each level of B, A and C are not associated. In other words, they're independent. We can see that from the absence of a directed line segment going directly from A to B. Panel 2 represents the mutual dependence of two variables on one other variable. A is a direct cause of B and is also a direct cause of C. In this case, B and C are marginally dependent and B and C are conditionally independent. Now consider panel 3. Here we encounter something new. C is a so-called collider variable. Collider because at least two arrows converge at this node. C is caused by both A and B. The diagram implies that A and B are marginally independent, but if we condition on C, A and B become conditionally dependent, meaning that within at least one level of C, A and B are associated. Now, it might seem to be nothing more than an odd quirk, but it will turn out that this slightly peculiar behaviour is both a bit of a nuisance and a key part of the story of how DAGs can help us to clarify the best way to identify a causal effect. We will learn much more about collider variables in the next lecture.